Okay, so today we're going to look at rates of change. Our learning intention is to gain the knowledge of how to solve problems regarding rates of change. We'll be successful if we can understand when we say rates of change, we are also meaning the gradient or the derivative. So it involves differentiation of a situation. Okay, so rates of change means gradient. It means differentiation. So we need to be able to know the difference between the average rate of change and the instantaneous rate of change. And we also need to know what is meant by the words displacement, velocity, and acceleration. Okay. So we learnt that the gradient between any 2 points is represented by the letter m, and we can calculate it by the rise over the run, so the difference in the y values, y2 minus y1, over the difference in the x values, x2 minus x1. So because we've taken 2 points and we want to find the rate of change between those 2 points, it's considered the average rate of change because we're taking the difference and we're trying to average it out. Okay, so imagine now having a quantity of something, and we'll call it Q, and if that changes over time. So some examples are bacteria growth in a culture, or the volume of water in a leaking bowl. So the volume of the water decreases as time goes past, or the distance of a traveling object. Okay. So we then say the rate of change, the average rate of change of this situation is considered the quantity, the change in quantity over the change in time. Okay. So differentiation. So we also know that the gradient of something is called dy over dx of the tangent at any point of a function. So any point in the function, we can figure out the gradient of that tangent by differentiating the function, yeah, and then finding out what that value of the tangent is at that point. And so this is called the instantaneous rate of change. So we still want to imagine there's a quantity of something, and we wanted to find how much that quantity has changed at a particular point in time. So we have to differentiate it to figure it out. So the instantaneous rate of change is dq, the change of the quantity over the change in time. So dq over dt. Okay. Here's an example. We have a hole. It's going to be dug by a group of work people. They remove V cubic meters, so volume of cubic meters of soil in T minutes. Okay, so they're digging a hole. So we want to state the domain of the function. That's what we're asked for. Well, in this situation, if time is 0, we'll have we wouldn't have dug any volume, any volume out, so we wouldn't know soil. So we want to figure out, so when t equals 0, we would have no volume. We also want to then figure out the maximum space of t. So if I'm going to use some algebra, the maximum volume, if I bring t squared over 20 onto this side, and 10t, if I was to, that'll be 2t would be 200 t. If I brought it back, t squared minus 200, so t minus 200. So the maximum that we have, the domain, will start from 0, so no time and no volume, to 200. So to take about the whole amount of to dig out the entire hole would have 200 minutes. Okay. So we want to figure out what the initial rate of work is. Okay. So we want to find a rate. Yeah. So this is, we're going to have to differentiate this with respect to t. So the volume, the change in volume, that's going to be 10, and that's 1 over 20 times 2 is so 1 over 20 times 2 is 1 over 10, yep, t. Okay, so we want to figure out the initial rate. So that's when initial means when t equals 0. Okay, and if we plug this in, the rate when t equals 0 is 10, because that would be 0. So 10 cubic meters per minute. Yep. That's the rate they will be working at. Alright. So what rate is the soil being removed at the end of 40 minutes? So we're just going to plug in when t equals 40 into our v dash. So 10 minus 1 over 10 when t equals 40. So 10 minus 1 over 10 when t equals 40 is 6 cubic meters per minute. And as you can see, from when the workers start to 40 minutes later, the rate of which they're working has a change. Okay. So that's the trick. So we're looking at initial rate is when we want to differentiate it. Okay. Here's another example. So the number of bacteria in a culture increases accordingly to the equation B equals 2t cubed minus 4t squared plus 200, where t is in the time in hours. Okay. We want to find the number of bacteria initially. Remember, the word initially means when t equals 0. So we want to figure out how much bacteria there is at the start. So if I plug in, so the number of bacteria is represented by this formula, 2t cubed minus 4t squared plus 200. If I plug in t equals 0 into the situation, I get 200. So there's initially 200 number of bacteria in the culture. Okay. Now we want to calculate the average rate of change, all right, between 5 and 7 hours. Okay, so that means that we're going to plug in when t equals 5 into this formula. Okay, I'm just going to, so 2 lots 5 cubed minus 4, 5 squared plus 200. So we'll get 350. And I'm also going to do when t equals 7. Okay. Alright, 690. Now we said that the average rate of change is the change in quantity over the change in time. Okay, so the quantity had changed from 690 minus 350 over 7 minus 5, so that's going to be 2. So the average rate of change to 690 minus 350 divided by 2, is 170 bacteria per hour. Yeah, and so that's the average rate of change. Okay. We want to now calculate the number of bacteria after 210 minutes. So what we're going to do is going to convert that into hours. So 210 divided by 60, so that's equivalent to 3.5 hours. We'll just plug that in. So B at 3.5 cubed, 3.5 squared, 200. So 3.5 cubed minus 4 lots of 3.5 squared plus 200. Okay. Yep. So we get a number of 230, approximately 236 or 37 bacteria at 3.5 hours or 210 minutes. Okay. All right. Next part says the rate of which the number of bacteria is increasing after 6 hours. So for this, we need to differentiate this equation. So B, all right, so it says the rate, so it means that we need to find the gradient when t equals 6. Okay, so we differentiate. 2 times 3 is 6, reduce the power. 2 times 4 is 8, reduce the power. Okay, so when t equals 6, b dash, or the instantaneous rate at this point, so 6 cubed minus, so we get 168. So the growth, or the rate, growth of bacteria is 168 per hour. Yep, or increase of 168 bacteria per hour. Okay. So some keywords that we need to understand. We need to understand displacement. And displacement is usually represented by the letter X. Okay. What it does, it measures the distance of an object from a fixed point, from the starting point. It can be positive or negative. So imagine that we have a ball, it starts at 0 and we throw it, the distance becomes that displacement. Or if you have a bottle of water and it's a liquid starts at some point, we've put in something else, another object, the water rises, so that change is the displacement in the water. Okay. As it says, represented by X. Velocity is usually represented by V, and this is the rate of change of displacement, how quickly this levels or this distance changes with respect to time. So that's velocity. It obviously involves speed and direction. So it is also the instantaneous rate of change of displacement. So the instantaneous rate of change of displacement is velocity. And so V equals dx over dt. Okay. Acceleration, well, that's normally represented by A. That's the rate of change of velocity of the rate of displacement, yeah, with respect to time. So it's the instantaneous rate of velocity, and so that's why A is dv over dt. Okay. Now we normally write rates as like this, kilometers per hour or meters per second. Now you can also write that in index notation. So we can write this as kilometers h to the power of -1. Yeah, because it's normally written as km over h. Well, h is just, as an index was h to the power of -1. So this is meters per second. That's how it reads. And obviously we have acceleration. We have kilometers per hour based on hours. Well, that's kilometers per hour squared. And we can write as kilometers per h to the power of -2. Okay, so you might see that notation in your books. Okay, let's do some examples. All right. Okay. So we now have a particle moving in a straight line so that its displacement, so how much it moves from its fixed point, 0 on a line at any time in t seconds is given by x equals t to the power of 2 minus 5t plus 6. We want to find the initial displacement, okay? So the initial displacement is just when t equals x. Oh, sorry, when t equals 0, not t. Yeah. So x means displacement. So all we're going to do is plug it in. So 0, 0. Okay, it's going to be 6. So it has moved 6 units or 6 meters when t is 0 initially. Okay. The initial velocity. Remember, velocity is the rate of change of displacement. So if we have x, if that's the rate of that's the displacement, velocity is that rate. So we have x dash. So that's going to be 2t minus 5. And if we want to find that's initial velocity, we want to find when t equals 0. We have the velocity is minus 5 meters per second. Okay. We want to then calculate when it first passes through 0 and with what velocity. When this first passes, so when the first displacement passes through 0. So all we're going to do is we're going to factorize that. So that's going to be t minus 3 minus 2. So when this is 0, using the null factor, we know that t has to be either 2 or 3 seconds. So the question says when it first passes, so it must first pass through 0 at t equals 2. So when t equals 2, we want to figure out what velocity it is. So the velocity we're going to plug in into this again. When t equals 2, so that's going to be 4 minus 5 is going to minus 1. So it's got a velocity of -1 meters per second. Okay, so that's 1. Yeah, that's that one. Okay. All right. So we want to then calculate when it passes through 0, through the fixed point 0, the second time. Well, that's obviously when t equals 3. Okay. And what velocity? So we're going to plug in 3 into this formula. So 2 times 3 is 6 minus 5 is 1 meters per second. Okay. Then the next part says when and where the velocity is 0. So remember that the velocity is x dash. That's dx over dt. That's velocity. So we want to figure out when that's 0. So 0 equals 2t minus 5. Bring the 5 across. We'll add 5 to both sides. Divide by 2 to both sides. All right, so that's when t equals 2.5. So when t equals 2.5, x, we want to find when. When was the 2.5 and where? So where we want to plug it back in here. X equals 2.5 squared minus 5, lots of 2.5, plus 6. That happens a quarter of a meter behind 0, the fixed point. Okay, and that's that example. All right, one more example. So we have a point. It's moving in a straight line. Its distance x, so its displacement from the origin 0 at any time where the displacement equals 2x cubed minus 15x t squared plus 36t. Okay. We want to figure out when its velocity is 0. So velocity, I'll do A over here. So velocity is equal to dx over dt, or x dash. And in this case, x dash is 6t squared minus 30t plus 36. We differentiate this equation. Okay, at what time is the velocity 0? So when is that equal to 0? Okay, we can factor out 6 on both sides, and then we can refactor this. So that's minus 3 minus 2. Okay, so it happens at 2 and 3 seconds. At time t. And he doesn't say if it's seconds or hours, so let's just assume it's seconds. We'll just say it's seconds. Okay, or units of time. Okay. We want to find the velocity and acceleration at any time. Okay, well, the velocity at any time is this equation, is x dash. Yeah, the rate of change of displacement. Velocity is the rate of change of displacement. Acceleration is the rate of change of velocity. So I'm going to write it as x double dash, or I could write it as, I could also write it as dv, the change of velocity over time. And all we're going to do is differentiate this. Okay, so 2 times 6 is 12, which is the power, and 36. Okay, so that is the velocity at any time, and this is the acceleration at any time. So maybe I'll just write velocity at any time, and then the acceleration at any time. Okay. We want to then find the initial velocity and acceleration. So the initial velocity, so that's when t equals 0. So initial means t equals 0. Well then x dash, if I plug in 0, 0 times it's going to be 36 units. And the acceleration, x double dash, is going to be 30 units. Okay. At what time is the acceleration 0? Okay, so when we want to find So when the acceleration is 0, so that's 0 equals 12t minus 30. 30 equals 12t. So t equals 30 divided by 12, which is 2.5. Okay. So what time is acceleration equal to 0? Well, that happens at 2.5. We want to find the velocity and position of this at the time. So the velocity when t equals 2.5 is, we're going to plug it into here. Is negative 1.5 meters of distance, or units of distance. Okay. And the position when t equals 2.5, we plug it into the original equation. So 2 lots of 2.5 cubed minus 15 lots of 2.5 squared plus 36 lots of 2.5, so 27.5 units. Okay, so its position is 27.5. The rate of change of displacement was negative 1.5, and that's when acceleration is 0. So part E, we will now figure out during what interval of time is the velocity negative. So remember, this is the rule of the velocity, okay? And so looking at that rule, we can see that if I was to graph it, it is actually a polynomial, okay? So we factored it out over here. So if I was to draw this quadratic, we have t here and the velocity here, so we've got 2 and 3, and we've got something that looks like that. Yeah, that's the velocity. So it says, during what interval of time is the velocity negative? So when is it below that axis? So that occurs when t is between 2 and 3 seconds. Okay, and that's the answer for these questions. Thank you very much.